So lift without ropes, how many shafts and cars are needed? Why do we want to make lift without ropes? It's very simple. It's about putting more cabins in one shaft and have more shaft efficiency. Actually, it's not new. A double-decker system is 2 cabins in one shaft, although they are linked together. Or we have the old Paternoster. It's a chain of cabins continuously cycling with 2 independent cars in one shaft, but there are still rope lifts. To put additional cars into the shaft, we will get a problem with the space and the ropes, and I'm not sure if this will be efficient, but to have the option to have multiple independent cars circulating in multiple shafts, it's better to have no ropes, and I want to concentrate on that kind of system. Actually, the idea of that is not new. At the last LF Con Lutfi, I presented a paper about a 2D elevator, and he described also a little bit about the technology, what is necessary. It's a linear motor, so the coil units are mounted at the shaft, and the magnet choke is on the cabin, and so the cabins can be moved independently. So we don't have a counterweight in such a system, so it's necessary to have lightweight cabins so that the energy efficiency is not bad. It's necessary to have the lightweight cabin. So another issue is the car guidance, and how can we exchange cars from one shaft to the other shaft. In that case, I'm talking about a backpack solution, and at an exchanger unit, the guidance of the car can be rotated, and so the car can change the shafts. And last but not least, but safety, it's very important. So when we don't have any ropes, I think everybody will understand. It's one of the main focus we set on, or we have to think about. If cabins cannot pass each other in such a system, it makes sense to have a look to the horizontal transportation, and in the similar system is the underground. Every train is stopping at every station, and this idea I would like to take to the vertical transportation. So, and use the circulating multi-car lift system as a shuttle lift in tall buildings, connecting the ground terminal floor with any transfer floors, and people can transfer to local lift groups. And that's not new, actually, to have transfer floors. It's a known concept to save the core space for the lifts. And with that, a traffic and transportation concept, the circulating lift system can be combined with traditional lift systems. If it's MRL, or is it 2 cabins in one shaft, or a double-decker, that's possible. But the main question is, what is the quantity of service and the quality of service of such a system, the handling capacity and the waiting time? I first want to start with the round-trip time of a car. The difference in that system is that the car is going up in one shaft and is going down in another shaft, but the round trip at the end is the same. But there's an additional time of changing between the up direction shaft and the down direction shaft. When we have a look at the round trip and we add a second car, we have a time between the first car and the following car. I call it the cycle time. And finally, the first car is leaving the main terminal floor, and after the cycle time, the second car, the following car, can follow. That means when we want to calculate the handling capacity, it's the well-known interval formula. So why is can you read here cycle time and interval? Because when you have two of these systems in parallel, then actually the interval is half the cycle time. So that's only the handling capacity of one system. And as we can see, the handling capacity is about the cycle time. So what is the minimum possible cycle time we can achieve? And for that we have to look at the stops of the cars. And actually it's on the one hand an intermediate floor, and at such an exchanger floor, and have a look to this exchanger floor first. So it's essential to have a good exchanger concept that supports low cycle times. And you can see the process of the exchanging them here. What is one benefit of that exchanger design is the preparation of the horizontal movement, the rotation, can be done in parallel with a passenger transfer, them entering and exit the car. And you can have a cabin in both shafts in that exchanger landing at the same time. So that supports a low cycle time. But the main issue is about safety distances and stopping distances. And in that graph you can see with the blue line, that's the normal position, and that's the position of a car during a normal travel. And this dashed line, that's the stopping point if a car starts a controlled deceleration with a jerk and with deceleration and the rated values. That's the point where a lift comes to stop. So as an example, when the lift is at that point in a specific phase of its a traveling curve, and the system decides to decelerate the car, it comes to stop at that point. So, but for a safety distance, that's not enough. At the end, we need an additional safety distance for the car height and an additional clearance between the cabins. So, and here we can see an intermediate stop. So this dashed line is the front car, that line is the following car, and the red line has the same shape like the stopping position of the diagram before, but with this additional safety distance. So, and this red line marks the safe position for the upper car. That means the position of the upper car may never or should never cross that safe position line that is given by the position and the traveling curve by the lower car. And out of that, we get a cycle time, and of course it's the standing time, it's the passenger transfer, the door times, and so on. And so we have that start to stop time that is mainly coming from that stopping point and safe position. So, how many cabins do we need? So, again, one round trip. So we know that's the round trip time, and that's the curve we have seen before, we know that after the cycle time, the lift will have additional positions, exactly these positions. But we also know that if the cars are separated by the cycle time, so we know that the front car has exactly, or should have exactly that position, and out of that we can make a snapshot of the current situation. That means that would be the position of each of the cabins. But what can we see is finally the number of cabins is the round trip time divided by the cycle time. Of course, we only can enter an integer number of cabins to the system, so we need to play a little bit with the round trip time, and maybe we need to increase the cycle time. But to change the round trip time, it's actually to change speeds and acceleration. To increase the handling capacity, it's the same like traditional lifts. We can use a double entrance floors, so we can load 2 cabins simultaneously. And the cycle time is then between 2 pairs of cars. And of course, they are still independent, these 2 cars, but they are some kind of linked together. To see the performance of a system, I would like to compare it with a double-deck lift system. So what is kind of a preferred system for shuttle, for a shuttle application? I want to have a look to different traveling heights. Each system gets 4 shafts. What we can see that the multi-car lift system needs less space. Why? Because it's only for eight passengers, so it's smaller cabins. It's also because of any the lightweight situation we have. Okay, the double-deck lifts have 2 times 16 passengers in that case study. The number of cabins in the multi-car lift system is variable. Of course, it's fixed for the double-deck, and the speed, of course, needs to be adapted according to the traveling height. So what are the chosen speeds? For the double-deck lift, there's 10 meters per second with 300 meters. What can be seen that the speed of the multi-car lift system is lower. With the results later, we can see why it is good enough to have a lower speed. What is interesting, there are no even numbers for the speed of the multi-car lift system. This is because of adapting the round trip time so that we can have an integer number of cabins and we have an optimum of the cycle time. The number of cabins, of course, it's a constant value for the double deck. At the multi-car, we need to add additional cabins to make sure that we can keep the cycle time as low as possible. The handling capacity, as the cycle time is constant for the multi-car lift system, the handling capacity in an up-peak situation will be independent from the traveling height. For the double-deck system, the round-trip time will increase because of the traveling height. That means the handling capacity will be lower. To achieve the same handling capacity would mean to add an additional shaft. The interval is again independent from the traveling height for the multi-car system, and it will increase for the double-deck system. When we look at the waiting time and transit times and time to destination. When the interval is constant or independent from the traveling height, then also the average waiting time is independent. And now what is interesting is that the time to destination for the multi-car lift system is similar or even better. And why? Because we have the short waiting times and we have an improved situation for the passenger transfer. We only need to transfer 8 passengers, and the analysis is done that people enter the cabin in the up direction shaft and they exit the cabin in the ground floor in the down direction shaft. So that means when doors are opening in the up direction shaft, we only have to add, or only the 8 passengers have to enter. In the multi-car, in the double-deck system, so when we don't have a 100% up peak situation, then first the down-traveling passengers need to exit, and then the 16 passengers can enter. So that means we have an improved situation at the loading station. I come to the conclusion. The maximum handling capacity of such a system depends on the minimum possible cycle time. The minimum possible cycle time depends on the stopping time and on safety distance constraints. Of course, the safety distance and what is possible needs to be calculated. The handling capacity of a system is independent from the traveling height and independent from the speed of the lifts. And we have a very low average waiting time compared to conventional lifts in a shuttle application. Of course, and that's according to Gina, always start with the calculation and then go to simulation. These results needs to be proven by simulation. Thank you for listening.